All right, well, here's a few news articles. Um, and, oh, I'm not sure about that key, Sonny. I don't remember, but wouldn't worry about it. Anyway, so this Microsoft Windows vulnerability that rated a 10 out of 10 on severity, apparently now their attackers are using it so they can get domain administrator on Windows machines. I haven't played with it, but it sounds very exciting. And everybody needs to patch their Windows stuff, which is, of course, a big deal, mainly for companies who run servers and have trouble patching them quickly. This thing looks pretty amazing. It's a little drone that flies around your house to take pictures of things and send them to you, and then it lands back in its dock to charge up again. So that way you can, if you're away from your house, you can dial in on your phone and fly around your house to make sure there's nothing bad happening in there. So sounds to me like it might have use for a lot of people. A lot of people are freaking about privacy implications, of course, if other people get access to it. But anyway, I would think this would be a big step forward from an ordinary security camera or a nanny cam, really. China has launched an asteroid mining robot, although this is just sort of an early stage where it's going to fly around and show that they can steer and chase down an asteroid and stuff, but still, that's pretty awesome. The one thing that I didn't notice here is any reason why you would bother. It's awfully hard to imagine that there's anything you can dig out of an asteroid that is worth the enormous cost, but I guess for scientific research it's there, and certainly for national prestige, as the United States continues to decline from a position of prominence and China moves forward to a position of prominence. I think they probably want to do this for national pride reasons, the same way we used to here. So here they wrote up how these people were able to take over the Instagram app entirely. And what they did is a supply chain attack. They found out that the Instagram app uses an image library from somewhere else, and that library had a vulnerability. So they were able to make poisoned images. They could email it to you, and if you open it in Instagram, it takes over the Instagram app. And the Instagram app has all sorts of unnecessary extra permissions. So that means that they can do all kinds of rotten things to you by taking over your phone. So it's a good thing to know about. And it's been patched now, of course. And so anyway, I got pretty upset when I heard about this last night. It hit all the news everywhere. Trump has declared again, probably more clearly than ever, that he has no intention of leaving the office. He doesn't really care about having an election. He doesn't see any reason why he should care about the votes. He should just stay in power forever, which is just what they say in other countries where they have dictators. And this led to a lot of things. Here's this guy writing about there are various things the Republicans could do to make this happen. The American democratic system is relatively fragile, and there are ways to elect. The Trump campaign and the Republicans have been in contact with people in swing states to arrange to have them appoint electors who will ignore the votes and just put Trump back in regardless of what the vote totals are. In addition to messing up the post office, so the vote by mail will be delayed or messed up, and coming up with many other ways to suppress the vote. So they're cheating in every way they possibly can. Trump doesn't care whether they cheat or not. He just plans on clinging to power whether he wins or loses. And so anyway, it's, many people are getting very upset again. He said an awful lot of things like this. Here's a sort of list of them. He is packing the Supreme Court with people who will be beholden to him, so that if he gets to complain and go to the Supreme Court, they'll vote for him, even though they ought to be recusing themselves. And he doesn't plan to pay attention to the term limits and stay on after his term is over. He's already tried to delay the election, but Republicans pushed back on that a little bit. So anyway, it's quite madness. And so anyway, I recommend make sure you vote. The only apparent way to do anything about any of this right now, since it does appear that we are going to have an election, although Trump has tried to delay it, other Republicans have not let him do that yet. So apparently we are going to have an election. It's going to be extremely manipulated and blocked, but if you should make the effort to vote, because if we have a large enough popular majority against Trump, then all of this after the fact screaming and really denying won't work. If it's close, then he will steal it. So that's why Bloomberg figured this out, and he gave him $100 million to Florida, because if Trump loses Florida, then it'll probably all be over, because there's no path for him to victory without Florida. But if he wins Florida, which he might, then there will just be a grueling battle over weeks and months with his supporters and Bill Barr trying to impound ballots that haven't been counted and declare them invalid, and just madness. So anyway, if you click here, it has details how to register to vote. Everybody should vote. This might be your last chance to vote. Anyway, here I see some, yeah, here's somebody put a link in the chat. Yeah, that's right. Get rid of the ballots and there won't be that's right. His point, he doesn't think there should be an election. He doesn't think there should be a transfer of power. He's just like he said last time, only now he's much more clear about it and much more scary about it. He's breaking the law every day, campaigning from the White House, holding illegal rallies in states that have denied them. And he's getting used to just ignoring the law and doing whatever he wants. And he doesn't see any reason for him to step down. This is what happens in many countries. And once somebody has power, they say, well, you know, why should I leave? I've got the power. And it's a real crisis in America now. And the best way out of this is to actually have a large voting majority vote against him. Then other than that, we're going to have a military coup or a lot of civil unrest, or it's going to be pretty bad. So highly recommend that you vote. If enough people vote, then we can hopefully hold off the worst of this coming crisis. Anyway, I've been hearing about this more and more, and it sounded really crazy to me, but people are saying this is great for malware. It's even great for pen testers. You go to an enterprise network, you hack in, and then you install an extra virtual machine on their network. Now, I guess the point is everybody's running a whole fleet of virtual machines, so you can sneak in one more without being noticed. And then your virtual machine isn't running any antivirus or anything. You can totally attack the network from that virtual machine. We start calling it shadow bunny. So you can either hang out in long-term persistence on your extra machine you've added to their network, which they may not notice, I guess, and then you can do cryptocurrency mining on your virtual machine and so on. So it's an interesting idea. Of course, if you could actually sneak an extra machine into the network and get away with it, that would be pretty awesome. And I guess you can these days. All right. And like I say, everybody is very concerned about the election, and with very good reason. Some people are saying you shouldn't talk about how you're going to cheat in the election because then people won't vote. But I think, if you have a large enough majority, then all the cheating won't stop you. And by the way, cheating is nothing new. There's always been 1 or 2% of cheating in American votes from one kind or another, ballot box stuffing, bribing people and stuff. But if you get a large enough majority, they can't overcome it by cheating, at least not normally. Anyway, this is pretty amazing. And see any else fun ones? That's what I thought was pretty amazing. They're a family of like 14 raccoons and then coyotes. They're everywhere. And because people are feeding them, they're getting to harass people and bite them and stuff. So the animal control people are saying, don't feed them. It's actually a crime to feed them. And if you do feed them, then they end up having to kill them because they become a pest. But they're sure coming out. The wildlife in San Francisco is really changing the way they act because of the lockdown, they say. And not sure I'm going to find anything else to talk about here. Got another minute. See anything else fun? I don't know why this guy doesn't run for president. Seems like he would totally fit in the Republican Party. This is Alex Jones. He's been banned from every social media platform he's out there. So anyway, he says Ruth Bader Ginsburg was sacrificed to Satan to give Democrats power. Can Windows XP lost support? Is there a way an XP machine connects to HTTPS servers? I have no idea. I didn't know there'd be any problem with Windows XP machines connecting to an HTTPS server. The fact that it's lost support, I don't think that would matter. I think you just have to put a relatively modern browser version on it. It's possible that would be a problem. It's a good question, and I don't know the answer. You could use Burp Proxy. I've done that before. And then Burp Proxy can downgrade HTTPS to HTTP. So you could run Burp, And BERT being Java-based code would probably run. I've done that before. So that would be the simplest answer, would be a proxy. Anyway, we're 10 minutes after. Let's carry on to the cryptography stuff. So that should be here. All right. So we're up to stream ciphers. And I've got some slides about that. All right. So there we go. All right. So we're going to talk about stream ciphers, the history of them, why they are the way they are, and then, of course, the flaws. Now, the point of a stream cipher is, instead of having a block of data, like 128 bits that you encrypt block by block, and then you have to somehow pad the input to fit in those blocks, you just have a long line of bits, random bits, and then you XOR that with the plain text, and you can continuously encrypt a series of bits, and it doesn't matter how long it is, and you encrypt things one bit at a time. So that's what goes on here. You have a mathematical algorithm to create a pseudo-random stream of bits. And like I say, all these things are essentially imitations of the one-time pad. If you could just produce random bits and transfer them and use them, that would be the one-time pad. And the whole point of this is, rather than having to distribute a whole one-time pad, you just distribute a key, and then you calculate these bits from the key, and they are close to just a random series of bits. And you have solved the key distribution problem. You made it simpler. You just have to distribute one key. And this is private key encryption, so you still do have to move the private key to the other end. So this thing is called the deterministic random bit generator. This is one way to do it. Where you have a seed, and then once you know the seed, you just get a series of random bits, but it's totally determined by the seed. This is how a lot of programming languages, random number generators, work. First, like C and Java and Python have one where you have to first call the seed, and you seed it with something like the time, and then you run from there. And that's turned out to be, of course, a weakness, because if somebody can guess what you're using for the seed, they get the whole sequence of random characters, random bits. So another way to do it is with a key and a nonce, where you use the same key for many messages, but you add a different nonce to each message, and the nonce is not secret. It's the same thing as the salt in a password hash, and then you send to the person at the other end the ciphertext and the nonce. And because they also know the key, they can reproduce the random bits. The point of this is, if you use the same key and you use a deterministic random number generator like this, if you use the same key for two different messages, then you're using exactly the same bit stream to encrypt them both. And if you XOR two inputs with the same bit stream, then you can just XOR the two ciphertexts, and large portions of it will come out clear. Any part where the other one is all zeros. So this is just like the two-time pad we talked about. If you have a random series of bits that you're using, like a one-time pad, it's fine unless you use it twice. And if you use it twice, its security plummets. So that's the issue. You can't reuse the key and the nonce. And that's the problem. Russia made this error in World War II. They ran out of one-time pads, so they started putting in more layers of paper and carbon paper to make more one-time pads and use them more times. And of course, if you can find two messages that were encrypted with the same one-time pad, you can totally crack it. And Microsoft did this. Microsoft Office didn't have any nonce at all. So if you encrypted two Microsoft Office documents with the same password, you could totally get in. And I was actually responsible back then in my company for telling them to encrypt stuff and use Microsoft Office and use a password, which we told our vendors, and use the same password for many files, because I thought we were making it more secure. And I probably was, in that it was better than what we were doing before that, which was sending stuff with no encryption at all. But it turned out to be a whole lot weaker than I thought it was. And so that's what we talked about last time, and I demonstrated it, and I'm happy to talk about it again if people try. But the point is, if you use a one-time pad twice, it's actually very easy to crack with a very simple attack where you just guess a few letters and gradually guess the whole thing. So anyway, so here's two types of stream ciphers. There's stateful ciphers with a secret internal state, where you have some internal state that keeps changing, and that's how it's generating the random numbers. Or you have a counter, where it just takes a series of counting numbers or some pattern of numbers. So you have a state, you initialize the state with the key and the nonce, and you update the state, and that gives you a bit, then you update it again and get a bit, update it again and get a bit, and on you go. That's the stateful stream cipher. There is a hidden state that you never see that is being used to create these bits. The alternative is counter-based, where instead of taking the output of each calculation as the input to the next, like you might in cipher block chaining, you just increment a counter. So you do a calculation with a counter and you get what a bit or whatever group of bits you're getting, then increment again, get a bit, increment again, get a bit, and on you go. Very, very analogous to counter mode in block ciphers and cipher block chaining in block ciphers. Now, the reason why these stream ciphers first became very popular is they were cheaper when decades ago, when these things started being used. Dedicated hardware is what was used here. You can have various kinds of dedicated hardware out there. These days, you hear a lot about ASICs, a special circuit just to do one calculation. The most common one these days I hear about is Bitcoin mining. And there's programmable logic devices and field programmable gate arrays, which are hardware that can be sort of adjusted to do one calculation in firmware and then do that calculation fairly fast. The fastest, of course, is an ASIC. You design the hardware chip to do exactly one thing and nothing else. And then, of course, in general, that's the fastest and cheapest if you have a large quantity of the same calculation to do. So this is what was done in the early days when people were not thinking about general purpose computers like Windows and Linux machines running software to do encryption. They were thinking about cash registers and financial devices, things to read credit cards and stuff, that you just have a little special chip right in the device designed just for the encryption. And that's what they were thinking about here. In software implementations, you are limited to using the official microprocessor instruction, and they typically do something like 32-bit words or 64-bit words, and there's only certain operations like add and subtract you have. So the algorithms that run efficiently are quite different than the algorithms that run efficiently on dedicated hardware. So the first stream ciphers required less memory and fewer logic gates than block ciphers. They work bit by bit. You'd build a special chip just for that. So you need 1,000 gate equivalents. That's how you rate the difficulty and expense of integrated circuits, is basically how many transistors does it take. And software-oriented block ciphers at this time would require 10,000 gate equivalents. So it was cheaper to manufacture hardware with hardware encryption chips that used stream ciphers. Right, but then DES came out in the 70s, and DES was optimized for hardware, the original American standard for encryption, and it used these 64-bit block and these S boxes, and we talked about it last time. It's this Feistel cipher where you encrypt only half the stuff and then flop it over and encrypt the other half. So this was designed to run fast in dedicated hardware chips. And it really isn't very fast in software. It wasn't designed for that. AES is the modern one in the modern age, and it's designed to run fast in software. Although, as we talked about it, a lot of people do in fact go back and add special AES circuits to their hardware, both to avoid timing attacks and to make it as cheap as possible. So ASICs are the fastest, cost thousands of bucks to get the chip, but then it's much faster for Bitcoin or anything else it's specialized for. GPUs are not as fast, but cheaper. And CPUs are very much slower. So that's when you go into cryptocurrency mining. There was a time when you could do Bitcoin mining on a CPU, but then everybody had to buy graphics cards. And now you got to buy ASICs or you're wasting your time, because the way Bitcoin mining works is there's just a race to mine each block. Every 10 minutes, somebody wins the race and gets a prize. And if you aren't the fastest, you lose. And if you're using hardware that is seriously slower, you will never win. You're just totally wasting your money. You're not competitive. So we can talk about a shift register. The left shift operation just rolls it to the left. So what you do is you start with something. If I have 8 ones and I roll it to the left one and feed in the right with a 0, then I now have this number, and one of these ones falls off the left. And that gives me an output of 1. Where's floating point gate array? FPGA, I don't know where it is. FPGA is certainly not as fast as an ASIC, but I don't know exactly where it is other than that. It's a good question, but I don't have a good answer. Caitlin's the expert. She uses FPGAs a lot. I've never used them. I've only talked about them. Anyway, so now you keep shifting it. So if you start with the register 170 and roll them off, first the 1 comes off, then the 0, then the 1, then the 0. So you're getting some bits, but if you're just filling it with zeros on the right, you're only going to get 8 bits before you just get all zeros. So that's a shift register. A shift register by itself just gets you as many bits as the size of your state there. So what you do is you make a feedback shift register, where you shift it to the left so a bit comes off and you calculate a new bit in some pseudo-random way. So with each update, you use the feedback function on the previous state to figure out what bit goes in on the right. So now you start with 1100, you roll it to the left, you get a 1. A 1 comes off, and then you recalculate a number on the right from this function. So you fill in this one, gets a 0, this one gets a 1, this one gets a 1. So you keep filling in the right with these pseudo-random bits. And the way you're getting them here is by just XORing all the bits. So if the number of 1s is even, you put in 0. If the number of 1s is odd, you put in 1. So now you get a longer chain of pseudo-random bits. But what happens is, just like the row function we did before with hash functions, even though in principle you have 16 possible values of a 4-bit shift register, in fact, you don't get a ring of 16 very often. What you tend to get is smaller rings. For example, if they're all zeros, then you roll off a 0. The next thing you feed in is also 0, because XORing all these remains 0. So this never varies at all. And the longest ring is in fact only 5. So it's not that great, but you do get some rings of numbers. So that's called a linear feedback shift register, where you take a function, which is just the XOR of some of the bits, and the longest possible period would be 2 to the n minus 1, because 0 is always going to just be sitting at zeros. So if you, in the most perfect case, this one would be sitting alone, and all the rest of these would be in one ring, and you'd get 2 to the n minus 1 possible values before it repeats. That's the best you can possibly do with a linear feedback shift register. All right, so here's another one where you XOR only 3 of the bits, not all of them. And it turns out this one's better. This one, well, it gives you a period of 6. And I think the best period we had the other way was 5. Anyway, so that's a linear feedback shift register. It is, of course, a very simple circuit, very easy to build, very fast to run, but it's not that great. All right, and here's the one with the maximal period with 3 XORs. All right. Anyway, and that gives you a 001 to 001. Here's 16 cells, and you went from here to there. She actually explored 15 possible values, all the values except 0. So it can be done. All right. These things are insecure, though. If you have 8 bits in the state, you only need to measure 8 values before you can predict all the rest. There's an algorithm called the Berkeley Mashi algorithm that does this. So they are intrinsically insecure. All right. So there are attempts to improve the linear feedback shift register, which is not that great. One thing is to add a nonlinear function here so that you combine them with a and an or in addition to it. And from this diagram, it's not quite clear where you put the output of that, but I think you include it somehow in calculating the next bit. So the point is these things are filtered, but it turned out not to be that great. There are more complicated attacks that tend to hit them. So what's considered better, rather than adding a nonlinear function on the side to the linear function, is just replace the linear function with a nonlinear function, where you use XOR and mix them together. So some complicated operation of combining the bits is used to calculate the next bit. And this can be much better, but it's such a mess, there's no easy way to attack it, no easy way to calculate how good it is. So the current hotness is things like Grain 128, where you combine the two techniques. You have a linear feedback shift register with a linear function here, and then you have a nonlinear feedback shift register here, and then you combine those two together with a filter function. This way, you hopefully get the best of both worlds. And this is pretty much what AES is reminiscent of this. This is what modern ciphers are like. You have a bunch of methods that are somewhat limited, so you just sort of do them all and mix them up. And then you've got something where all the simple attacks won't work, because the attacks would only get one part of it, and they wouldn't be able to get the other part. This seems to be working pretty well in the modern world. So that's Grain 128, and that's supposed to be very good. It has a 128-bit key and a 96-bit nonce, and it has a period of 2 to the 128 minus 1, which is really, really big. We've talked about this many times. 2 to the 100 is essentially an unthinkably big number. You could never try 2 to the 100 keys or store 2 to the 100 bits of memory or do 2 to the 100 anything. So anything with 2 to the 100 is pretty much infinite. You can just, that's so big that you can use it forever. So this would be very good. All right. And so the linear feedback function is this strange thing where it takes various bits scattered all over the place and XORs them. And the nonlinear feedback function is a ridiculous mess. You've got linear terms and terms that are multiplied together and terms that are multiplied in 2 and 3s and 4s. So it's really very nonlinear. And the end result of this is the bits are effectively random. So the early version of it from 2006 had a side channel fault attack, which means I think if it makes mistakes, you can get information about the key. And the newer one from 2011 appears to be unbroken. Very good, although it's not being used that much, but it does exist. So we have a system available. A lot of people are still using older insecure systems. All right, so A51 was intended for cellular telephones. So it was used in 1987. Now, the phone company followed the same rules as the military at this time, which is they like to keep their algorithms secret. Most cryptographers don't like this at all. They say it would be much better to use a well-known public algorithm and keep just the key secret than to keep everything secret, because if your algorithm is secret, it's likely to be insecure and old and weak. But they did keep it secret for a while, but it leaked eventually. And so, and of course, it was because they wanted it to be weak and cracked. Then they made an export version, like there was in most things in the 90s. There's a deliberately weakened version. But anyway, A51 leaked in 94 and was reverse engineered in 99. And it was used quite recently for essentially all the phone customers in the world. And it has serious weaknesses, which we'll talk about here. A51 uses 3 linear feedback shift registers of various sizes and then just XORs them together. So here's the functions they use. They're all just linear feedback shift registers. And so, however, instead of updating all 3 at once, it has a pattern of update this one, update that one, update that one. It takes certain bits to decide which one to update, which is, one could regard it as a nonlinear activity. Anyway, the ultimate total amount of secrecy here is 64 bits. You have a 64-bit state. So you could try all the 64-bit keys, and that's only 2 to the 64 operations. But I don't think, all right, that's possible, but not very practical. That's a very painful activity, doing 2 to the 64, but there are faster attacks. There are subtle attacks and there are brutal attacks. You can attack the 2 to the 64-bit key in the 22-bit nonce. You can brute force the internal states, but if you do this, it only takes 2 to the 52 operations, which is beginning to be feasible because the fact that it's broken up into these little chunks makes it possible to solve smaller problems that add up rather than solving the whole problem all at once. As we talked about before, sort of like a meet in the middle attack. But the brutal attack uses time-memory trade-off. Now, if you tried to make a rainbow table of 2 to the 64 bits, that would be nice, but you can't afford 2 to the 64 bytes of RAM. But what you can do is you can put part of the calculation pre-calculated and then do part of it in CPU. So you can do time-memory trade-off in the middle where you make it faster. So these guys used 2 months to make a 2 terabyte lookup table, and then they were able to decrypt in nearly real time. They were able to make the calculation simpler and faster. So they totally cracked this thing. And I remember I saw some DEF CON papers at the time, and I really sort of freaked out because even a 64-bit key is really quite secure. And I remember they said, we are going to crack a 64-bit key in real time. And I said, they aren't going to do that. There's no way to do that. But in fact, they did. They can. You do it by moving part of the calculation into a rainbow table. And it's quite a clever mathematical trick. So anyway, A51 was abandoned for 3G and 4G, and they now use a different block cipher. People are concerned that the NSA has a secret backdoor into it, but as far as I know, there is nobody that can decrypt it on the fly outside the NSA, and that's what we're using now. I don't know about 5G. I don't know what encryption they're using. I would imagine it's still the same thing, but I haven't seen any paper telling me what they're using. Let's take a look at the cahoots. This is chapter 5A, I think. Yeah. Try and get the right ones. Loading pin, my goodness. Okay, Kahoot is slow today. Filtered LSFR uses, no, that is a nonlinear feedback shift register you put there in the chat, Unstable Jimmy. Filtered just uses linear and then passes it through a filter function later. And I wasn't quite clear exactly how that works. Echidna. Echidna is just a, well, I'm thinking of echinacea. I guess I don't know what echidna is. Echidna, maybe a fish or something? I'm not sure. Anyway. Possibly a flower. I'll give it a few more seconds. All right. All right. What stream Cipher uses? Init and update. Those are stateful functions. You initialize the function and you keep updating the function. This is also how hash functions work, which we'll talk about later. All right. Which cipher was designed for hardware in the 70s? That's DES. Kind of wonder if it might be true of A5 also, but it's certainly true of DES. Anyway. All right, what system can be broken with the Berkeley Mashi algorithm? Ah, a spiny anteater. All right. All right, that's the linear feedback shift register. All right. All right, which system uses an LFSR and an NFSR? That's grain 128. You mix the two together and you get something that's considered quite secure. So Juarez and Echidna will have to tell me who they are. R will have to tell me who they are if they want their points. All right. All right. Ha, all right. All right. So I'm going to, Kahoot changed your name. That's interesting. All right, I'm recording these names. I didn't know Kahoot would change your name, but I guess they try to filter out what they interpreted as swear words or something. Anyway, all right, good. I got your names. So let's carry on here. All right. Anyway, so then we're going to talk about the software stream ciphers, which are more what's commonly used these days. The point is, uses general purpose computers that have a 32 or 64-bit word. And so stream ciphers have become more popular because they don't, this padding turned out to be a problem. Cipher block chaining was really popular until the padding oracle attacks came out. And then people realized that padding was not such a great idea. RC4, Ron Rivest, who made a whole lot of these things, the R in RSA, made this thing which is very clever, very fast, very simple, and was popular for a long time. It's fallen into disfavor recently. This is a really crazy system. I really like it. So what you do, and by the way, say, starting about 5 years ago, everybody finally got fed up with it. There were all these series of RC4 weaknesses until everyone has pretty much said you shouldn't use RC4 for anything anymore. But it was everywhere. RC4 works in a very simple way. You have 256 bytes. You start out with just every byte in an array. And all you do is you shuffle those things around like a deck of cards. There's no formula or XOR or AND or anything. So your key, you start with a key, and then you just take the key to determine which two cards to flip and go through every byte of your key, and it indicates a different card to flip. So this is very much like what happens when you shuffle a deck of cards. Flip two cards, flip two cards, flip two cards. You shuffle those things around, and then you've got a key stream. So you generate M bytes of key stream like this by flipping cards around, and then you can just XOR that with your plain text to get the message. It's very simple, very fast, very easy to do. Yeah. Anyway, so this was used by double wide equivalent privacy. All payloads use the same key but a different nonce. The problem is RC4 was not designed with a nonce. All there is a key. So what they did was just treat the first 24 bits of the key as a nonce. Now this is a no-no. When you're using cryptography, don't decide to re-engineer it so something designed for one purpose is used for a different purpose. You will likely be very sorry. And we'll see here when we talk about authentication systems and ways to move associated data, you know, you can't, this is what went wrong with the padding oracle. People were taking the fact that you could encrypt something as authentication, and it's not really the same thing. And so here they tried to take the first 24 bits of the key as a nonce, and that turned out to be a really bad idea because of the birthday attack. If you have 24 bits of randomness, you only have to do 2 to the 12 guesses before 2 of them will happen to collide. That's the point of the row, Pollard's row that we were doing. If you have n possible values, by the time you have guessed square root of n at random, you're likely to have a collision. So this means all you have to do is catch 4,000 frames of wireless traffic, and you'll find 2 frames with the same nonce. And if they have the same nonce, then they're encrypted with identical key streams because you're using the same key. So now you can just XOR those together to find out information. And so that turns out to be a really bad idea. By the way, the nonce is at the start of the key, and that means the first 24 bytes of the 24 bits of the key are known because you send the nonce in clear text. So you're actually leaking information about the key. So this turned out to be a really bad idea. And there are many other attacks against WEP because WEP has a whole lot of data that is very repetitive going over wireless network. You can guess which frames are the ARP frames by their size, and you can guess most of the bits in the plain text in an ARP frame, so you have a known plain text attack on top of all the rest. So there are many, many ways to crack WEP. WEP was ratified in '99, but by 2001, there were serious attacks, and people cracked it more and more and more until it is pretty worthless. You can crack into WEP in less than 5 minutes with ordinary hardware. And I don't know if anybody's using it anymore. My students and I used to war drive San Francisco looking for WEP networks, and they got down to like 1% a few years ago, and we couldn't do it anymore. It's pretty much gone extinct, not because everybody wised up and learned cryptography, but just because WPA came out, and all the modern hardware is WPA, and very few people are still using equipment so old that it runs WEP. At least that's my feeling. Anyway, the problem is it was also used by TLS, which is on the web. TLS doesn't try to add a nonce, and so it uses a complete 128-bit session key. So you'd think 128-bit private key encryption would be very good. And it would be if the only thing that mattered was the key size. If you had to try all 128-bit possible combinations, you would never get in. But the problem is RC4. That shuffling cards thing is not random enough. The second byte is 0, 1/128th of the time instead of 1 in 256 at a time. So it fails to be white. This is called spectrally white, where every value is equally likely. And it fails in a really serious way. And that means you can totally hack it. Public exploit's been around since about 2011. All the first 256 bytes are biased, of course. If one of them is more likely to be 0, then of course all the rest are not white either because they skewed the probability. So all you have to do is catch a really large amount of encrypted data, like millions of encryptions, and then do a statistical analysis, and you can deduce things about the key because it's not white. There should be no pattern in the ciphertext. If there's any pattern, that gives you a lever you can use to go back and deduce something about the key in many cases. So that's the point. And by the way, here's another fun statement. The first key stream bytes are more likely to be 0 than any other value. So if you just collect a large number of encrypted packets and see what the most common ciphertext is, the most common value of ciphertext is the plain text, encrypted with a key of 0 that does nothing. So in fact, it's leaking out unencrypted data. These are pretty monstrous flaws, and that's why everybody's pretty fed up with RC4. But there's been quite a while doing it. People, all this whole series of attacks, until they finally got one that they said the no more attack and said, all right, quit using RC4. This is really terrible. It's not that, you know, you have to get millions of encrypted requests, but in practice, it's too unsafe to use. And so everyone is now pretty much telling you to knock it off. Although even this serious one, you had to take 75 hours at thousands of requests per second to get enough millions of packets to deduce the key. So there are better stream ciphers out there. Salsa 20 is one of them. And here's a variety of ones, grain and so on. There's a lot of these new ones. Salsa 20 works like this. You have 512-bit blocks, and you increment a counter for each block, and you have a key, nonce, and a counter, and so on. So this thing here is considered a lot. Yes, TLS1 is bad because it uses RC4. I think that's correct, yes. The early versions, that's one of the many problems with it. Now, there are a lot of different ciphers, and I don't think they all used RC4, but now all RC4 versions have been removed from modern versions of TLS. They're not approved anymore. Anyway, so this uses a thing called the quarter round function, where you take, you have 4 32-bit words, and you combine them this way, and you shift them to the left, and then XOR them with each other to calculate new values. So this is just a way to transform them. And you've got bitwise rotation. If you take a number like this is 32 bits written in hexadecimal. If you shift it to the left by 8 bits, that's moving one whole 2 characters over. Each one is 4 bits, so the 7 moves over 2 spaces, and the 0, 1 rolls around. 16 bits would move it over 4 spaces, so the 4, 5, 6, 7 goes here, and the 0, 1, 2, 3 there. If you move it by some other number, like 22 bits, then some of the bits from this nibble leak into another nibble, and you get totally different numbers, 59C and so on. So that's bitwise rotation, which is a very simple transformation. And so here's what you do. You've got keywords and nonce words and counter words and fixed constants. So you have a 4x4 array of 32-bit words. And then you're going to scramble this whole thing. And this is very similar in its general outline to AES, which we'll go through in considerable detail later. These are the modern ways to do it. And so you have a series of transformations where you transform the rows in various combinations. So you scramble it this way, you scramble it that way until you've pushed all the patterns out. And so this quarter round function is one of the functions that scrambles these things and moves them around. And you know, I'm not too worried about all the details. You have 20 rounds of it. And the point is, it really does scramble the bits so you can't figure out the key from the output. And you can even evaluate its security by having less rounds and attack them. And people have found that if you have 8 rounds or fewer, you can find some information about the key faster than brute force. But if you use 20 rounds or 12 rounds, it's considered very secure. So 20 rounds is the more secure version and 12 rounds is the less secure version. And they're both considered very good. And we'll talk about this. AES uses 10 rounds and is considered very good. And it looks very similar in general outcome. And you see all these things just take the simple transformations like XOR and shifting things to the left and shifting things up, and just scrambled these operations together in a way that is hard to reverse. So here's things that can go wrong. We talked about this before. If you use the same key and nonce for 2 plain text, then you got the same problem as the 2-time pad. That ruins everything really fast, and a lot of people made that mistake. WEP did it by accident by using too short a nonce, so before long the nonce would happen to be reused. Microsoft Office did it by having no nonce at all over and over again. Here's a broken RC4 implementation in code, because this thing here has a way of calculating the new values of these two internal states, it doesn't consider the possibility where the two bytes are the same, where I equals j. When I equals j, the result of this code is to wipe out one byte. So this has a weakness that it looks good for a while, but it has a mistake, and eventually it slowly destroys the internal state and turns into all zeros and stops encrypting entirely. And that's not a fundamental flaw of RC4, it's a flaw in this code. And that's, of course, another issue. Even if you have a secure cipher like AES, it's very likely that you can make a coding mistake coding it. So that's why the general rule is never write your own cryptography. Find a standard library and use it. You'll be a lot safer. But then you have to update it when they update that standard library. So here's all you can have weak ciphers baked into hardware. This is, I mentioned before, you'll probably hear it again. The whole cryptographic community is very, very angry at the government because they deliberately forced people to use unsafe stuff. And decades later, that stuff is still out there, and there are still systems that can be downgraded to the old stuff. So again, this A52 is like export grade cryptography, and it is a shame, of course. So if you use the export grade, then of course you can hack into it because it was designed to make it possible for the NSA to spy on it. And that's why you have all cryptographers in general are generally on the liberal side of things, saying the government should just give up being able to read everybody's email and listen to everybody's phone call, and instead let us have some privacy and get it down to where they can only do targeted surveillance on people after writing a search warrant, instead of just expecting to hoover up all the data on the internet, which is what they've gotten used to doing. Anyway, so it's 5B. All right. By the way, TLS1 has other problems too. TLS1 does not have forward secrecy. So if you save the data and get the key later, you can get in. So there's a variety of, and there's a variety of defects, but RC4 is one of its defects. I don't see the echidna. I think someone might still be coming. I'll give it a few more seconds. All right, I guess this is it. All right, what system inserts a nonce into the key? WEP did that, which is why when I first got WEP decades ago, it said there's two modes, a 40-bit mode and a 104-bit mode, but the 40-bit mode is also called the 64-bit mode, and the 104-bit mode is also called the 128-bit mode. And I said, what is this nonsense? And that's because the first 24 bits are the nonce. So your 64-bit key is really only 40 bits of key and 24 bits of nonce, which they expose. And boy, I didn't know enough details to be horrified at the time, but when you deliberately publish part of the key in plain text, that sounds awful. And of course, it is awful. Anyway. All right, what system uses a quarter round function? Okay, that's the salsa 20. All right. And which one uses a session key to protect cookies? That's TLS. It uses public key encryption to create a session key, which it then uses AES and encrypts the data from that point out. At least a lot of versions use AES from then on. All right, what system has 12 or 20 rounds? That's salsa. Good. All right. So Juarez, all right. And SO, have to tell me who they are if they want their points. Z, all right. Same story there. All right, good. I see a name for Z. All right, I'm gonna, what encryption for regular phone RC4, non-slight padding? No, well, I'll answer those. Let me just stop the recording.